just read the first part of the procedure, did some descriptions. It says repeat the treatment of the precipitate with another 10-drop portion of ammonium sulfide, and you add that to the first one. Okay, centrifuge and decant, save the decantate in the stopper test tube until we get to procedure 11. Okay, so that gets saved for 11. The precipitate, turning the page, and this is the thing people always miss at the top of page 184 because nobody reads the whole page, they always jump to the next procedure. At the top of the page 184, it tells you to wash the precipitate. It's the same sort of thing you did when you washed the precipitate at the end of 5C. You're going to add some water and ammonium acetate. The reason you're putting in the ammonium acetate, and the reason I say it's 4 times better, this has nothing to do with protein. This has proteins too. And we're using it in this sense. What it means is the precipitate breaks up and it goes into suspension. And you can't centrifuge it, you centrifuge and you look and it still hasn't gotten clear. That means it's peptides. To avoid, and it's a colloidal suspension. So to avoid that, we put in some strong electrolyte like this, and it diminishes the charge on the surface of the precipitate particles so that they can stick together and centrifuge out. The reason the colloid is stabilized is because all those little particles of the precipitate develop electrical charges, and then they start repelling each other, and they stay in suspension. You centrifuge, and nothing happens. So the ammonium acetate helps prevent that. Okay. So you wash the precipitate, and they save it. You go to procedure 7. Okay. And here's where you're going to start separating out your ions. The first thing you separate out is mercury. And one of the nice things, if you're stopping at this point, you can start the process of dissolving your precipitate with the dilute nitric acid. Don't use the concentrated, by just adding it to that and letting it stand over the weekend. Now don't stop her too tightly because it makes NO gas and everything, so you don't want to build up pressure inside your test tube and have things pop and forth. So you just stop her loosely. But you can start the HNO3 procedure right in your test tube if you have to go home at that stage, if you run out of time. Then you come back and continue, and you put it into the casserole, and it says boil gently for about a minute. And I always say about 5 minutes because you want to make sure this gets all dissolved. And if you started with the 3 molar HCl in the test tube already before you go home, it's going to slowly dissolve at room temperature over the weekend or whatever, or the next lab period. Okay? But you still want to put it in the casserole, make sure everything's complete, boil gently. Now the big problem we have in Chem 1B, students don't know the word boil gently. They put it right into the flame and they look 3 seconds and everything's gone. That's not boiling gently. So when you're boiling gently, here's your casserole, here's your flame, and you can see the liquid bubbling a little bit in here. You don't pop it directly into that hot flame because it's going to evaporate away completely. If you ever saw these fancy little chemistry slides and things, they actually make really small burners. They're about this big, and they get a really small flame, and you put your casserole over that, and you're not going to boil everything away. And they charge a really big price for those. It's twice as much as one of the little burners, I guess. The micro burners cost a lot more. That's why we don't have them. So you just have to be careful. You know how to do this, right? You don't get it too close to the flame, it won't get too hot, and it won't evaporate away. So you're boiling gently, and he says 1 minute, I say 3 to 5 minutes. And the important thing here, that's an L, it's replenish. You always want to have about 15 to 20 drops of 3 molar HCl in your casserole. So as it goes down to 5 or 10 drops, you add some more 3 molar HCl. Because if it gets too concentrated, what's going to happen here, this is separating out mercury 2 sulfide and of course the sulfur. This will never dissolve. But if you get the acid too concentrated, this dissolves too, and then you don't find your mercury. So what you're doing is you keep it fairly dilute by replenishing with 3 molar HNO3 from time to time. And you replenish with acid, not water, just because you're using up the nitrates and the hydrogen ions as you're dissolving your precipitates. Now in your known, if you have copper, copper always has a pale blue color. The nitrates may be such a light blue color you might not see it. You should, for this one, for the medium amount, you should definitely see a little bit of copper ion in solution. It should have a slight bluish color. And you should have, what color is this?
Black.
Black. Right, still black. Okay, so you should have some black precipitate. Now if you have a lot of sulfur, you may just see a sort of grayish one or brownish one, but there's still black in there. If you have no precipitate and it's completely yellow, you don't see any indication of black at all, this is your unknown, it's probably a pretty good indication what? Your unknown doesn't have mercury 2 ion. Okay. So this is, I'll leave this up. The rest of the confirmatory step is pretty straightforward. Oh, it's not pretty straightforward. But these you can say for procedure 8. I'll talk about procedure 8 the next time so you can get somewhere today. But this, you go on to the rest of the procedure. The key thing, the other correction you want to watch down here, near the end of the paragraph where you're doing the confirmatory test, it says 2 to 5 drops of tin 2 chloride. You want to put in 1 drop of tin 2 chloride. If that makes a precipitate, you stir it up, centrifuge it, and look at the amount. Okay? Near the bottom of the paragraph in procedure 7, just above the notes. Then you can add a second drop. And if you don't see many more precipitate forming, and you start seeing your original precipitate get smaller, don't add any more tin 2 chloride. I'll talk about the net ionic reactions for that the next time. Okay, somebody had a question. Do you still have your question? I still haven't learned all the names. You still have your question? Did I cover it? Okay, then I want to look at one other question here. This is in the related problems that go with the silver group. I know it's in here, but I do this every year. Here we go, problem 915. It's on page 167 in this edition. Student was given a silver group unknown, was told correctly it contained only 1 cation. And it says she treated, because they changed that from E to E to the student or whatever. Treated with 6 molar HCl, as directed, made a white precipitate. She washed this precipitate twice with cold water. Then she treated the precipitate with 1 reagent. Which reagent should the student use, and what will happen with each of the 3 different ions? Answers. What the student has is either this or, in other words, the student has one of these 3 white precipitates. There's 1 reagent you can add that will tell you what one it is. What reagent? Well, when you think about 4A, it tells the difference between these 2, right? You add NH3, This gives you black precipitate. When you add it to this, what happens?
White.
Dissolves. Okay. And by the way, this question came up because I mentioned this in lecture, and somebody already asked me about this. Notice if you ask me things when you're doing your known, I will tell you as much as I know, or as much as I can tell you. But when you're doing your unknown, and I realize you're doing your unknown, and everybody was doing their unknown yesterday, except one person, yes. But, and when I say yesterday, this means the last lab. Coming back to this thing, it said, well, the book says gray to black. And I said, the reason it's gray, it has an impurity. Because when you react this with the ammonia, remember I said you make equal amounts of mercury, which is black, and the mercury 2 amide chloride, which is white. The resultant mixture is still a black color, not a gray color. How do you get the gray? You have that black mixture with something else that's white. This is white. You didn't get all your silver chloride out. It'll be mixed with your black precipitate, making it look gray. That's easy to handle. You add more ammonia, and it should eventually dissolve all the silver chloride. But here's the kicker. You didn't get rid of all your lead in procedure 2, and with the washings and everything, because you didn't treat it with hot water. And I told a couple of people when I was looking at their precipitates that it was somewhat smaller than it should be, and chances are it was smaller than it should be because they didn't do the hot water treatment long enough. Okay? You got to make, and you can, actually it's not how long you do it. It has to be hot when you take it out of the centrifuge and separate. If it's cooled off and you can touch the test tube, you're not going to get a good separation. After a bunch of washings, you will eventually get rid of all the lead. But the point is, lead 2 hydroxide is a white precipitate. It does not dissolve in ammonia because it's also a base. So if that's mixed with the black, it will give you a gray precipitate also. So that's how you can tell the difference. You either get a white precipitate, everything dissolves, or you get a black precipitate when you add ammonia to that single precipitate. You can't do that because you might have both of these, or all 3 of them. Right? That's why you have to go through the entire procedure. Okay, I'm done talking. Any questions? Let me get your keys, turn on the